Okay, so problem solving with graphs. Okay, so I'm going to show you a problem, and this problem has appeared on CS interviews, and I don't know if it still appears. So, problem solving in graphs is not just important when you go to the real world and need to solve problems, but if you need to get a job, you need to do well on interviews. Okay? So I'm going to show you a drawing of a park divided up into grid squares. Okay, so let's make a nice big park. Okay, nice big park. It's divided into grid squares, 25 grid squares. Okay. Think of some kind of a map of a park where you've grid squared it, and each grid square has an elevation, so I'm going to write down the elevation. 3, 2, 17, 11, 12, 4, 1, 18, 10, 7, 21, 22, 23, 16, 8, 20, 13, 599, 599, 25, 24, 6, 14, 15. Okay, so each grid square, think of it as maybe some hilly. The park is a hilly park, and there are elevations at different locations that correspond to the grid squares. Okay, now the high level task when this problem was asked is we need to place drainage at various points in the park, and we need to determine how much drainage is going to occur. So here's the model. Okay, on each grid square is going to fall 1 unit of rain, and when a unit of rain falls, for example, the unit of rain falls on this square, its elevation is 17. That unit of rain is going to look around and see where's the direction of steepest descent, and it's going to drop to the lowest elevation neighbor that it has. So 17 will drop to 1 because 1 is the lowest elevation neighbor. Okay, and so look at this. So 17 will flow. From 17, the unit of rain will flow to 1. Okay, and so you can imagine that. Okay, so the question is, given this model, where do you place your drainage, and how much drainage do you place? Okay, and the obvious answer to this question is to say, well, let's look for the lowest elevation because all water flows downhill. We're going to look for the lowest elevation here, and we have 25 units of rain, so we need to place 25 a drainage capacity of 25 at this spot. Okay, it's a reasonable solution, but you got it wrong. And if you did that in the interview, who knows? Okay, you may not get the job. Okay, so one way to solve this problem is to sort of think about it and just analyze the park in the following way. Let's draw an arrow from each square to where the water will flow just from that square. Okay. So basically what I'm doing is I'm treating each grid square as a vertex. Okay. So I'm treating each grid square as a vertex. Okay, think of it that way. Okay, each grid square is a vertex. Okay. And from the vertex from this vertex 17, it flows down to height 1. Well, we can immediately say that all the neighbors of 1 will flow down to 1. So this guy will flow down here, that guy will flow down here, this guy will flow down here. All these neighbors will flow to 1 because that's going to be clearly the lowest. And we might wonder, well, does everything flow to 1? And that's the interesting question. So, for example, let's look at this 20. What surrounds this 20? Well, you've got a bunch of high numbers and a 13. So this 20 might flow to the 13, but look, where does this 13 flow? This 13 flows to the 5. And then from this 5, 5 is the lowest elevation that's reachable from 5, and if you look just at the neighbors. Okay? So water that flows ultimately to 5 is stuck there. It's kind of like a ridge. It's a local valley. So if you put all your drainage here, then you're going to have a flood at 5. But let's continue and put in the arrows. Okay, so that's sort of what we sort of what we sort of understand by asking the question, does everything flow to 1? Let's continue and place all the arrows. What you see is that we're building a directed graph. Why directed? Because the water flows only one way. It can't flow from 1 back to 29. It flows from 29 to 1. So we're building a directed graph. So let's continue. Okay. So 20 flows to 13. 13 we know flows to 5. That's the lowest elevation neighbor. What about this 25? Its options are 20, 24, 13, so it's clearly going to go to 13. What about this 24? Its options are high options, but the lowest option is 5. Okay. What about this 6? The lowest option is 5. What about this 14? The lowest option is 5. Oh, this is interesting. What about this 19? Again, the lowest option is 5. Okay. Now, let's look at the other squares. Well, what about this 15? Its lowest option is not 5 because it can't reach 5 in one step. It's actually going to flow to this 9. Okay. And what about this 9? Its lowest option is actually this 8. Okay. And what about this 16? You might think, well, does it go to the 1? No, because its lowest option among the available options is this 5. So it has 5 available. Everything else is larger than 5. So this 16 actually flows to the 5. Okay. What else can we say? Okay, the 8. Where does the 8 flow? Its lowest option is actually 7. Okay, so the 8 flows to the 7. Okay, let's keep going. What about this 12? The 12 flows, its options are 11, 10, 7. So the 12 flows to the 7. The 11 flows to the 7. The 10 flows to the 7. Okay, and now for each square, we have attached a directed link to the square to which the water will flow from the original square. So, okay, and what we have done, as you can see, is built a directed graph. Okay, and once we have built this directed graph, the solution should pop out at you. Okay, it should pop out at you that, oh, there are connected parts of this graph. There's the red part, there's the green part, and the blue part. Okay, and the solution should now sort of suggest itself that, oh, and there are some vertices, there are some squares which only have incoming arrows. That means that water comes in there and has nowhere else to go. All the other squares, for example, the 9 has a square from 15. 15 will flow to 9, but both of those will flow to 8. All 3 of those that come here will flow here and then stop here. There's nowhere to flow. Okay, so where do we need the drains? We need the drains. We need a drain at 1. Okay. At this elevation 1. We need a drain at the elevation 7. Drain at 7. Okay, and we need a drain at the elevation 5. So I drew my problem with all distinct elevations, so the elevation tells you where. Otherwise, you'd have to specify the location, like an x and a y coordinate. Okay, and what are the capacities of the drains? Well, you just need to look at the size of the part of the graph that flows into that drain. Okay, so for the red drain, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the capacity should be 9. Capacity, okay, so I'll write the capacity here. The capacity here is 9. What about the green drain? Well, the green drain has 1, 2, 3, 4, 5, 6, 7. That part of the graph has 7 squares that are all linked together by arrows. So the capacity is 7. And what about the capacity of the blue drain at 5? It needs a capacity of, so look at the part that's connected by the blue arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9. Capacity 9. 9 plus 9 plus 7 is 25. So the total capacity is 25, but it's not all going at the elevation 1, the lowest elevation, which might be the simplest solution that pops out at first. But once you formulate this problem as a graph, the correct solution also pops out. Okay? And so that's the solution. But the lesson here is, when you have a problem to solve, and you're thinking graphs, what you should think about is there a relationship here? In this case, the flows down to relationship. Is there a relationship here that I can, use to formulate a graph? And then maybe once I formulate it as a graph, the solution will either pop out, as it did here, or I can use tools that we have developed in graph theory, in graph algorithms to solve the problem. That's one of the skills that is very important for a computer scientist. Okay, so today we discussed graphs, we introduced notation, we talked about the handshaking theorem, and very importantly, problem solving by massaging the problem, putting it into a graph format, and then using what you know about graphs, tools, and algorithms to solve the problem. See you next time.